Now, let's see what angle OPQ is from here. That implies angle OPQ is angle OPA minus angle QPA is what I get when I take this to the left hand side. Now, as I clearly see here, angle OPA is 90 degrees because OP is the radius and AP is the tangent. So, radius is perpendicular to tangent. Therefore, this entirely is 90 degrees. Therefore, OPA is 90 degrees and my angle QPA is X, is what I get from the diagram. But as I clearly see here, I get that my angle OPQ is nothing but 90 minus X. X is already substituted to be 90 minus X by 2, which we have already proved for X, which is 90 minus theta by 2 is what we got. So simplifying this further, I get this to be 90 minus 90 plus theta by 2. Therefore, this on cancellation gives me theta by 2, which clearly makes me understand that theta, which is angle PAQ, therefore substituting for theta, angle OPQ is angle APQ PAQ by 2. When I further simplify this by cross multiplication, angle PAQ is twice angle OPQ is what I get from the given proof. Therefore, angle PAQ is always twice of angle OPQ is how they are connected. Similarly, proceeding with the same proof, taking this angle, that is angle OQA is OQP plus PQA, and then going along the vertex Q in the similar manner, I prove that similarly I get angle PAQ or QAP is twice angle OQP, which I can prove through the similar proof. Hence, these are the two properties which are identified for the external tangents drawn from an external point A, where the angle between the tangents theta is always twice of the angle between the radius and the chord of the either angles, which I get as OPQ and OQP, which are always half of the given angle PAQ. Now let's see the last property in connecting the tangents to the circle, the extended property out here. So let's take a circle in which I want to draw for each of the point of contact. When I draw the tangents, I get a quadrilateral ABCD where the points of contacts are PQ, RS. That is a quadrilateral which is obtained by connecting each of the tangents drawn at PQ, RS on the circle is what I get with the circle, of course, inside the quadrilateral, because the tangents are always outside the circle touching the circle. Therefore, the quadrilateral obviously should lie and circle inside and a quadrilateral outside. So with this quadrilateral, I would like to prove that my required to prove part out here in case of this quadrilateral is that I had to prove AB plus DC is equal to BC plus AD. That is, when I add the opposite sides in pair, they must be equal in case of this quadrilateral. So my proof is that I have to prove AB plus DC equals BC plus AD is what I need to prove in case of this. So as I clearly see here that the proof is totally reliable on an external point from where two tangents are drawn. That is, when I take each of the vertex of the quadrilateral ABCD to start with the vertex A. Now, the first vertex of the quadrilateral ABCD is clearly passing through two tangents. That is, for an external point for the circle, there are two tangents AP and AS which are equal, because we have already seen the property that from an external point, the lengths of tangents are equal. Therefore, AP must be equal to AS. Similarly, BQ must be equal to BP. This must be equal to this, and this must be equal to this. Is how we get each pair equal to the other, because the lengths of tangents from an external point are equal. So using that condition, let's prove AB plus DC equal to this. So let's see how we can do the proof of this theorem. So considering the proof, let me consider AB plus DC on the left hand side and prove the right hand side from the LHS. So LHS being AB plus DC is what I considered, and clearly when I take AB, I can split AB as AP plus PB. Therefore, I can split AB as AP plus BP. When I add together, I get AB, as can be seen from the side AB. Similarly, I can split the side DC, because DC can be written as DR plus CR, which on the whole makes the whole of DC. Therefore, splitting DC as DR plus CR is what I get when I split each of the sides AB and DC through the respective points PQ, RS, or P and R. Now here, AP is clearly equal to AS because the lengths of tangent from an external point A are equal. Therefore, AP is equal to AS. In place of AP, I write AS, as can be clearly seen through the lengths of tangents, this being equal to this. So AP equal to AS, I replace AP with AS. Similarly, my BP is equal to BQ with the similar property. So therefore, in place of BQ out here, I write BP. Instead of BP, I write here BQ is what I write here. Similarly, when I have DR is nothing but equal to DS, therefore in place of DR, I write DS. And lastly, CR, which is equal to CQ, I write here CQ for each of the properties. Now next, what I do is I compare